All right, so we discussed how to improve like the memory issue or the computational issue to a certain extent, right? So let's now start discussing about something that's known as the algorithmic efficiency. And so what is this algorithmic efficiency? Well, whatever we do, like we got rid of like a lot of things, like a lot of data points, and we talked about training set consistent and so on, right? But like regardless, we are still finding the nearest neighbor, right? So we have to find the nearest neighbor. And so can we get it to a certain extent more efficient? Meaning, can we find this nearest neighbor quickly? Like, so basically, can we converge to the final solution as quickly as possible? One way of doing that is something that's known as the branch and bound algorithm, and that's what we're going to look at in this video. So branch and bound when finding the nearest neighbor. All right. So there are a few assumptions, and we are kind of assuming that we have this like pre-processing step that involve like putting data into a nice, and we talked about that a little bit earlier, right? We said that like this pre-processing step may involve putting data into a nice geometric form and do something with it. And we're doing some like basic, let's assume that we have this pre-processing already done, maybe, or maybe the original data is something that looks like this. So what am I talking about? Well, I'm talking about like the data distribution itself. Let's say these are some data points, right? And then this is like my entire data set. You can tell just by looking at the data distribution that there are like, although I'm drawing a very nice clustered sort of structure, but you might have something similar to that, right? So imagine we have like this two sets of data called clusters. And so the first one can be defined as, and so this is the other cluster. So let's say this is S1 and this is S2. And so the attributes of these clusters are that the center for S1 is denoted by mu1 and the center for S2 is denoted by mu2. All right. And obviously they, like each one of them will have some radius, right? And so I'm denoting this by R1 and this I'm denoting by R2. All right. So the question arises again, how do we get this data in this form? And we'll address that soon. As I said, there are ways of getting it, maybe sometimes in many applications. The data itself is like this. Okay, so let's now get back to the branch and bound because we want to find the nearest neighbor quickly. All right, so when we are finding the nearest neighbor, the one thing that we need is the test point x, right? And let's say this is like my test point x and I want to quickly find its nearest neighbor, right? So what I'm going to do is I'm going to jump into S1 and find the neighbor that's closest to this point. Let's say this is like, this point is the nearest to my x, and I'm denoting it by x1. All right, so basically the nearest neighbor that I found to x is x1. Maybe we can consider it temporary for now because a closer point might lie in S2 as well, but let's keep this for now. And so I have these two options of like jumping into the cluster S1 or S2, but I chose S1. And so this is my branch step. This is exactly my branch step. I got down to like, I had the choice of like two branches. I got down to one of them. Now I have like this X1. And if I try to repeat this for a point in S2, then I will eventually be doing this for every data point, right? If I'm trying to do like which is the nearest neighbor. And so of course I've been looking at like some points here and then some points here, there. And so this is not really efficient, right? What I need to do is I want to bound this search somehow. So is there, obviously, whenever we're trying to do something like this, we need to come up with a criteria using which we can determine a bound, right? And as such, like the closest point so that we can check quickly whether we even need to jump into S2 or not. So can we bound this search? Because like basically the idea is that I should be looking at every point that is the nearest neighbor, but I don't want to do this because I'm looking for efficiency. And so I need to bound this. So let us assume that the closest point in S2 from this x, any point which will be like the nearest, is essentially x, this x minus mu2 minus R2. You can tell like it has to lie on somewhere on the surface and like very close to my x. So based on this, we can come up with something that's known as the bound criteria. Let's look at what is the bound criteria. So any nearest point should be at least like x minus mu2, because this is the center, minus r2, lying somewhere here, right? This is what it needs to be. So if I can ensure that this x minus mu2 minus r2, I should have written r consistently so that we don't get confused, minus r2, right, is greater than or equal to, at least like greater than the distance of this like x, whatever the test point is, from the point that I figured in my S1, right, and then obviously the estimate, right? If I can ensure this, then I mean, there is no other point that has a shorter distance than the one that I found in S1, and so that I don't need to search S2, right? Because this is greater than the distance we found. So essentially what we have established in this bound step, and this is the bound step, that no further search of S2 is required. And what have we done? What have we accomplished? Well, we have saved ourselves, I would say we have saved ourselves of searching the entire data set. So there is no need, if this holds, right? So there is no need to search S2. Excellent. So with these steps, like the first and the second, right, what we have accomplished is the branch and bound algorithm. This is a known algorithm. This is known for its mechanism that is guaranteed to work. All right. But of course, like we'll have a few observations that we'd like to note down here, and let's note those observations down here. So what are those observations about this branch and bound? It finds my nearest neighbor quickly, and it is guaranteed to find the nearest neighbor. So it produces the nearest neighbor, and that's guaranteed. All right. And we can do this recursively. So we can find this nearest neighbor recursively using this algorithm. A quick way of like also showing why this recursion really helps is that, let's say my S1, in which like I'm trying, this is my test point X, and let's say within this like cluster there were like these small clusters or like the data distribution or something like this. So what you can do is, like, if S1 had more clusters within it, then we can run this branch and bound hierarchically within, like going in S1 and then seeing and then finding the bound condition and so on, right? And so based on this, like the worst case runtime for this algorithm, the worst case runtime is order n. That is when, like, every time you check and then the bound fails. Every time you check bound, it fails. And so you have to search, like, this is the worst case. But in most practical situations, it's better than this, right? So in fact, it has been a big research question, I would say. And some of the research questions are framed around, can we relax this a little bit? Because like in the worst case, of course, I will be looking at like endpoints, and then it's not really doing much of a like favor to us in that sense, right? So one research question is, can we relax these conditions a little bit? Can we do something that's to get a better algorithm? And that's like, of course, it's faster, it's quicker. So can we relax something? Well, the short answer is yes, maybe yes. So maybe we can say that with high probability, my runtime is not order n, but or like logarithmic. With high probability, my runtime is logarithmic. And that, of course, depends on like the pre-processing of your data, the way the data is coming to you, or maybe you relax certain other conditions, right? So sometimes the data is such that you expect it like the runtime to be logarithmic, but there are some other ways also to improve, right? Another way is to like when you're relaxing, you can say that we want an algorithm that finishes quickly, of course. That was the whole point of branch and bound. But let's have this nearest neighbor that is closer, the closest nearest neighbor, by some factor of the actual neighbor. So I'm like not really wanting this exact X point, but like maybe somewhere here so that I don't have to look at like every point in the other cluster. Somehow, maybe I can like do something that helps me not really getting this like n number of steps. So these are some of the ways in which we can like further improve. And in either case, we have to consider like E out. Be like really cautious, because we have to think about E out, whether we are getting near optimal or not, because that was the whole point of the nearest neighbor algorithm. Okay, so these are some of the important observations that accompany the branch and bound algorithm. Now, going back to our algorithm, our question, like one question that we might want to answer is that when do we gain in our algorithm? I would like to summarize this first. Yeah, so that there it is, finding the nearest neighbor. This is like summarize whatever we did. So this is the test point here, and then of course I branched it based on, like, I had two options, so I branched it, went to this branch, and if I could somehow establish this condition, I can bound it as well, right? And this branch and bound can be applied recursively, and we also talked a little bit about how we can improve things. Okay, so as I was talking about, like, what is that sufficient condition based on which we can say that, yes, I have gained? And this is more from an intuitive point of view. Like, the question that I'm trying to sort of answer is, like, when exactly in the branch and bound do we gain? Okay, so when do we gain? Or, like, when does the bound hold, in other words? To like understand that, let's like quickly draw the clusters that we had. So this was my mu2, the radius was r2, and this here was my mu1, and my radius was r1, and this was my point x, right? So basically we know that this distance, and if we found any point here, we know that that's going to be like x minus mu2 minus r2, right? So any point there. And similar to that, we can have, like, and this, by the way, was my x1, you remember, right? And so we observe that, like, we observe this thing that, and this can also be a distance, by the way, right? So this can be mu1 minus mu2, right? And this here, this point here exactly is going to be, this distance, this entire distance is going to be x minus mu2. All right, so all of that is known, and this exact is going to be x minus x1. Okay, so this, because like this distance here is x minus x1, the nearest point in this S1, right? So what we're observing here is that my x minus this x1, whatever it is, right, is indeed less than any other point in my S1, right? Any other point in my cluster S1, and that's why I just like went ahead for that point, right? And so any other point would lie in this range in my cluster 1. Now, like any point within this cluster 1, this is like any point in cluster 1, right? So if we are somehow able to establish, right, x minus mu1 plus r1, right, is less than always to any point that's nearest to x in my cluster 2, like this thing here, right? We know that this entire distance is x minus mu2, and so if I subtract this r2 from that, right, then I get like the distance of any point, like maybe x star or whatever you like to call it, from this, right? So if that nearest point is still further away from any point in my cluster 1, right? So basically, like in mathematical terms, I can say x minus mu2 minus r2, right? If this is the case, then it is guaranteed that we are going to gain in this like branch and bound, right? So this is the sufficient condition. This is the sufficient condition. All right. So let's rearrange things here, and just like a word of caution, this is for the, like, we are trying to come up with a heuristic. If you think about it, this is not like a mathematical fact, because I am looking at these clusters that are like positioned in a certain way, and so I'm looking at only certain types of data sets, right? And so this is a heuristic, but still this gives us an intuition about like when we gain. So that's the whole point of doing this analysis. So I'm just like going to rearrange these terms a little bit. R1 is less than, okay, so this is the same thing I'm writing, minus R2. If I just like rearrange the terms a little bit, what I'm going to get is like R1 plus R2 is less than x minus mu2 minus x minus mu1. Okay, so what is this, like x minus mu2 and x minus this distance versus this distance from the center, right? Now, if my distance from the center of cluster 1, which is like x minus mu1, if this is like really, really small, maybe in certain cases we can say that like my x minus mu2 and x minus mu1 are like, x minus mu2, if this is like really small, then we can say that this x minus mu2 is like almost equal to, or it tends to, mu1 minus mu2. What was this x minus mu2? It was this line here, right? And so if this is like x minus mu2, mu1, which is like this distance is really, really small, this line kind of comes in somewhere here, right? And so it like comes really close to this mu1 minus mu2. So that's what we're trying to say. Like this goes in and maybe like overlaps this, or not quite, but like comes really, really close to this x minus mu2. So if this happens, then what we arrive at is something like this, like r1 plus r2. And again, this is not a mathematical identity, so to say, but this is going to give us like a good view of when we gain. All right, so when will the bound condition typically hold? When this thing holds. Okay, what is this telling us? Like, okay, so this is, or maybe you can say that this is when it's expected to hold. That's another like better way to put it. So R1 is the size of cluster 1, right? R2 is the size of cluster 2. So R1 plus R2 is measuring within cluster spread, or you can even say inter-cluster spread. So this is like oops, no, I don't want that. Okay, keep, shouldn't be doing these things. No, I don't need subtitles. All right, going back. Okay, so I don't know what I did. Basically, let me do this. R1 plus R2 is my intercluster, and mu1 minus mu2 is between cluster spread, right? Or it's also known as intra. Let me just write this much. Intra-cluster spread. All right. So the overall intuition coming here. So we already talked about all of this. This is the bound condition, and then this is the sufficient condition, and most likely it suffices to say that the within cluster spread, right, should be less than the between cluster spread, right? The branch and bound algorithm is likely to give us good results if the data can be stored in first of all, sets of these form that are tight clusters and well separated. This is what this means. They are tight and well separated. This is what this means. So from the perspective of like getting better results in branch and bound, you should try to save your data in these clusters that are well separated. This is what this is like trying to point at. Now, how do we get these clusters? We have something that's known as the clustering criteria, and there is an algorithm that finds clusters in data. And like basically what we'd like to have is like this condition being met. And the best we can do is like we can have like something like R1 plus R2 being really, really smaller than mu2 minus mu1, right? So that like the between cluster spread is really small, and the within cluster spread is all the time larger than that, right? So we can get a tight and well separated data, and there's an algorithm that helps us do that. So we want to get clusters that get this condition. Okay, so let's look at that algorithm. What are we waiting for? The algorithm is known as the Lloyd's algorithm, and pretty well known. You might have come across that. How does this work? Let's say this is my data. And then the data is like randomly distributed and it's all over. And I'm going to pick some centers randomly. So let me pick this one randomly, this one randomly, this one, and this one. And then depending on like some input that you want. So pick some center randomly, first of all. So this is step 1. And then like pick the, so how were we, this actually means like pick the first point, right? And then pick the next point as far as possible and keep doing that. So this is what I did, like pick the next point that's as far as possible to this one, and then pick the one that's like as far as to this one, and so on. So keep doing that, like pick next as far as possible. And again, randomly doing that, right? And keep doing that. So these are known as our centers. We are picking them far apart because we want the clusters to be well separated. Now what we'll do is we'll construct the Voronoi regions. So we are like aware of that around every center. So maybe something like this. And so in every, and let's say this was the point and not this one, so that it looks, right? So we'll get these like well separated regions. We have seen these before. So let's say there was one here. And so we're not going into the details of that. And finally, I got something maybe here. I don't know. Maybe I got this. Like this is the Voronoi region. Doesn't look really nice, but this is the best I can draw. Anyways, now what we'll do is the third step, once we have the Voronoi regions possible, and then the Voronoi region, the third step is going to be update the centers. So I already have these centers, right? So I'm going to update these such that, because obviously I'll have some data in each region, right? I'll have some data. So there will be like the correct center somewhere, right? So update the center to the point that is the actual center of that cluster, right? And then maybe figure out the radius of each cluster so that, for example, let me write update the center to the actual center. So once I have the actual center, I can figure out the radius, right? So I'll have like some kind of clusters in here. That's what I'm trying to say. So based on that, I can figure out the radius that just like fits this region. Okay. So after we get the radius, like we have these clusters that are well separated regions because we explicitly attempted to make my R1 plus R2 to be less than like within cluster, which was like my mu1 minus mu2, right? So this is one way of doing that. And this is known as the Lloyd's algorithm. This is all that is to the Lloyd's algorithm. All right. Let's look at this example. So this algorithm is to find clusters. And of course, this is like shown here in a more, I would say, a better way. And you can see these like overlapping regions, but these are the formulas to compute the centers and the radius. And like usually the data in like many applications is already clustered. So you don't need, because if you look at this data that we're looking at, this is like the worst case possible. Data is like everywhere. There are no clusters whatsoever. And so this was like a difficult one to do. That's why we have like these overlaps. And so we have to figure out which are like which cluster, which one belongs to. And again, there are ways to solve that as well. But this was like a very random, like distributed with no clusters at all. Well, the good news here is that, believe it or not, many like applications have already like clustered data. So that's good news for us because when we already have clustered data, then we can actually get these nice, I would say, nice regions and well separated centers, and then it's easier to get the centers and then easier to get the clusters. And then we can use whatever we did earlier, the branch and bound, apply that and get the nearest neighbor quickly. All right. So with all these algorithms, let's try to kind of summarize what we did and where do we go from here. So what we did was like we were trying to pick like based on some K, we were trying to pick, let's say this is like my data and I'm trying to like this is X and I'm trying to find the nearest neighbor. And of course, like in this cluster, I was trying to find some point within this cluster and then do something with it, right? So another, based on my K, of course. So now another issue, like because I've decided my cluster based on some radius, like some parameter, right? So what happens if there is some data right here, right? And that could have been like a better, maybe, I don't know. I mean, maybe that had some other classification and maybe this was like even a better sort of, I don't know, way to classify my test point, right? So I'm getting like in this, I'm getting, first of all, making my nearest neighbor really efficient by getting rid of a lot of data. So I'm like taking away a lot of data, that's fine. But then situations like these can arise in that case as well. Let's say I started working with this data and I got rid of like these points and maybe there was some information that was useful there, right? So is there an algorithm that uses all the data to classify X? Or maybe now we saw that if we are using like all the data, that's bad, right, in terms of memory and efficiency and so on. So maybe we can weigh them in a way that the closer data points to like X have more weights versus the ones that are far away have less weight, right? So that kind of an approach where we can like kind of give some sort of weightage to weights depending on where exactly their positioning is with respect to the test point is known as something that's called radial basis functions. And that's exactly what we're going to look at in the next lecture. In fact, we are going to keep some of the approaches that we talked about in today's lecture, and we're going to extend that approach to derive the radial basis function. That's going to be the next lecture, lecture 18. So thank you.